Good morning, everyone. Today our team will be discussing the project that we worked at for the past 8 months. Our team consists of myself, Noah Allen, and my colleagues, Crystal Mojica and Finley Turnier, and we are proud to present a modular upbuilding prosthetic for children. Now, it should first be noted that the field of prosthetics is extensive, and as such, the focus of prosthetics for children was split between two teams, according to the two regions of the body. Our team decided to take focus on the upper limb region, and another team decided to take focus on the lower limb region. Now, it's been recorded that children have been rejecting prosthetics at a rate of 10.9%. This has been attributed to the fact that the device replacement normally takes place 6 to 12 months after the initial fitting. Many factors have contributed to this, however, device health growth is the predominant reason. Now, to resolve these issues, we created a device, a below-elbow prosthetic limb device that satisfied two goals. It was targeted for children between the ages of 5 to 12 years old, and it incorporated adjustability of limb length and addressed the issue of discomfort. As you can see from the table below, between the ages of 5 to 12 years old, there's about 11 centimeter limb difference. For our model, that's too large of a gap for us to factor in, so we decided to divide this age group into two subsections, 5 to 8 years old and 9 to 12 years old. So for our project, we're focusing on the 5 to 8 years old model. Now, the division responsibilities are as follows. I was responsible for fabrication and documentation. Chris was responsible for testing and documentation, and Finley was responsible for engineering design and documentation. Now, to clearly define our project objectives, we divided our project into two phases. The first phase involved us modeling the prosthetic using appropriate CAD modeling software, such as SolidWorks and ANSYS. And in doing so, we conducted engineering analysis by comparing and contrasting materials that we could use, assessing the physical limits of our design using finite element analysis, and optimizing our design before furthering on with prototyping. Now, for the second phase, we developed a terminal device. In our case, it was a hand. In doing so, we wanted to make our testing more human-like, and for this hand, we actually created a mechanical driving mechanism for it as well.
In order to develop a functional prosthetic marketable to amputees, we had to abide by standards set by both the health system as well as engineering standards. In general, prosthetics are classified as in classes, and our prosthetic is a class 1 type prosthetic. The regulating body that determines whether a prosthetic can be brought out to the market is the FDA, and the critical standards that were used in the design process of pretty much the same standards as they relate to the process of making plastic parts as well as the testing methods of plastic materials.
At onset, we established design alternatives for the socket and the wrist. After researching different types of sockets and forms of attachment, they include the blown open socket, silicone suspension, Falcon suspension, also integration. We decided to proceed on with the blown open socket. We chose this socket based on the fact that it was originally designed for children. It weighed between 100 and 200 grams, equivalent to the average weight of an apple. The advantage of this type of socket include that it's adjustable and it's easy for throwing and doffing. Adding a wrist to the component will increase its overall performance by increasing its range of motion and its functionality. Here are different images describing different types of wrist joints. The second image described here is the type of wrist joint that we implemented into our design, which is a twisting mechanism.
Now, our final design can be summed up into these key concepts: affordability, lightweight, tractability, functional grasping, and hand dexterity. In phase 1 of our design, we pretty much incorporated the tractability of the prosthetic. That was the main focus point of phase 1, and that required us using the asymmetric data as a guiding element to fit the dimensions as well as meeting the demands of appearance and capabilities of the prosthetic. Now, in order to overcome the challenge of using that asymmetric data as well as conforming to capabilities, we had to take multiple iterations. At first, we used that asymmetric data to form a mold for the forearm, and then conform that mold to a residual limb. Then third iteration, we conformed the different segments and we joined them together. And fourth, we finally came to a final design by optimizing repetitive. Phase 2 pretty much added functionality to the prosthetic. By adding an appendage, we were able to incorporate techniques of a mechanical slider, ratchet gear and ball, and pins in order to add the grasping ability for the overall prosthetic. And using asymmetric data, we was able to pretty much conform the size to an actual size of the age group that we were targeting. Now, the tools that we use are ANSYS and SolidWorks to pretty much carry out a lot of our analysis and simulation. Pretty much these tools help us validate our design as well as optimize and provide preliminary testing prior to manufacturing. And stage one pretty much was focusing on the forearm and brace, and stage two was dynamic testing of the wrist mechanism as well as the pin to gear reactions. Now, as you can see, this was a setup of our forearm, our main focus point, to see how we can design a concept whereas the forearm is capable of retracting and extending while being able to provide enough, being sturdy enough to actually support the child's weight. Setting up, finding balance, and constraints are all part of the final element analysis. You have to find the correct balance in order to mimic the actual scenarios of how a prosthetic would actually be used. Now, multiple benchmarks were tested. We used a bending test and a tensile load, and using von Mises stress criterion, we were able to determine a factor of safety for both loading situations. Now, after multiple iterations and getting multiple results, we found areas where, weak points where we can optimize. And iteratively, we found the best design, and we ended up with a minimum factor of safety of 4.8 in bending and 15 in tensile loading. Now, similar tests were carried out for the socket. Now, the aim for the socket was to be able to find an optimal material that we could actually conform to the shape that we wanted to actually design the socket, and then find material that's actually liked. So we tested multiple materials. We tested aluminum, 2 types of aluminum, 2 types of steel, and we decided to go with stainless steel. And because they gave us a maximum displacement of 1.02 millimeters, as well as a factor of safety well above 30. Now, phase two, adding appendage, what we concentrated on was seeing if the concept can actually work, as in the pin to gear reaction. Similar to a ratchet and pawl, we pretty much saw what would happen when we applied a torque to the finger and see if the pin would be able to prevent the finger from extending or retracting. And the pin to gear reaction and wrist sliding mechanism all worked as they were supposed to work. And the kinematic motion study allowed us to see that the pin pretty much had a minimum factor of safety of 3.3. So failure will most likely occur in the pin. That's what we determined, because the gear pretty much would shear before the pin would snap off.
So for the manufacturing of the main body of our prosthetic, we resort to 3D printing. We mainly chose 3D printing because of its easy accessibility, its quick production time, and also because it had a price that met our budget. Now for the CAD mold parts, we had the forearm, hands, and gear fabricated by a 3D printing company within the area. The screws, washers, nuts, and bolts used were already available to us, so they're not listed. However, for the fabrication of our tensioner and fastener components, because they were custom made, we had to shop around to receive price estimates, and we found out that depending on the type of fabrication, it would range from $400 for the parts altogether to even $400 per part. So the team decided to take it upon ourselves to utilize our access to nearby machinery to fabricate the components ourselves, and in total it took 2 to 3 days to complete. Now this is an exploded view of the forearm unit, where the upper and lower forearm molds are both made of clear plastic, and they're separated to show the tension and the fastener components, both cut from aluminum, and they're used to secure the forearm and store the elbow socket brace inserts. Now the elbow socket brace is made from stainless steel, and the screws, nuts, and bolts are also made from steel as well. Now this is an exploded view of the hand, where the wrist, palm, and the fingers were made from PLA plastic, and they're secured by the screws, nuts, and bolts. The driving mechanism of the hand, which was the ratchet and pawl system, is comprised of the gears, which were made from ABS plastic, and are driven by aluminum pins stemming from the wrist and to each finger, excluding the thumb. Now for the construction of the forearm unit, we printed four molds in total, 2 for the upper forearm and 2 for the lower forearm. These molds were designed to be fitted into one another and then secured by the tension fastener and their respective components. Ideally, our final mold, the prosthetic, will be sealed all around to prevent separation of the unit while being used by the child. Now for the construction of the hand unit, the wrist, palm, and fingers were printed. The palm served as a casing for the mechanical driving mechanism, and it can be removed as necessary to maintain the drivers. Now, the motion of the fingers, so the motion of the fingers was established by placing of joints on each finger, and the wrist unit served as an entry point for the forearm connected to the hand, and it also possesses the interlocking mechanism which secures the forearm to the hand.
We designed 3 different experiments that are primarily focusing on the hand. These experiments include the range of motion, range of function, and a loading test. Range of motion, we explored different open and hand-closed positions possible for the prosthetic hand. Range of function, we explored different configurations that the prosthetic hand might have. And for loading tests, we explored the deflection that the prosthetic hand might have under different loading and different lengths. Range of motion results are based on the hand grip positions that include the open palm grip, the power grip, and the open position grip, just to mention a few. However, all these positions demonstrate its own purpose and its own functionality. The most critical, most practical of these positions include the hook grip and the open position grip. The hook grip allows the user to hold a cup and hold a bag, while the open position grip allows the user to hold small objects. For range of function, we evaluate the ability to grasp and maintain possible positions while holding small objects. We also evaluate the ability to hold an object while being used. We consider the prosthetic arm to be a cantilever beam. We wanted to mimic the idea that the prosthetic arm being attached to the residual limb. Therefore, different lengths were measured, different lengths of extension were measured that included 0.20 inches, 0.39 inches, 0.59 inches, and 0.59 inches. During each of these extension lengths, however, loads were applied that ranged from 1 to 10 pounds. In order for us to evaluate our experimental data, we applied Castellanos theorem to analyze the deflection for our certain conditions. Here are different tables describing the theoretical and experimental data achieved. Trials 1 and trials 4 are compared. In each of these tables, it describes the maximum loads and minimum loads and their respective deflections. As you can see, they're different. The deflections isn't really off, which demonstrates the overall performance of the prosthetic arm and our proof. Here are different tables describing the theoretical and experimental. Each of these lines demonstrates the different extension lengths possible of the forearm region. As you can see, basically, higher deflections was caused at maximum extension.
So for our prosthetic design was geared towards children coming from low-income families and or not having insurance that could afford them a functional prosthetic. So to keep the marketability of our prosthetic in mind in a global perspective, we intend to outsource our design and the needed software to various health professionals. And doing so, all that's needed is the amputee's residual limb dimensions, and these dimensions can be entered into said software, which would then render our default design to accommodate the amputee.
The material that was chosen was PLA plastic. The manner in which it is stored is very crucial, as PLA plastic is not able to withstand temperatures or high temperatures. Its melting point is between 173 to 178 degrees Celsius. However, usually around 120 degrees Celsius it begins to deteriorate. Safety precautions must be taken. An adult must physically evaluate the prosthetic arm before any usage for any wear and tears, as it can cause direct and indirect damage to the user. Based on the IEC standards, we recommend that the user give a test trial between 5 to 10 minutes before any usage to get used to it. In case of any allergic reaction to the materials, we recommend that the child use a residual limb over their, we recommend that the child use a sleeve over the residual limb. In case of for sanitation purposes, water and mild detergent can be used.
Now, another important part that we really wanted to look into was to see how creating this product would pretty much impact the environment and sustainability. Using two methodologies developed by Institute of Environmental Sciences at University of Maryland and tools for the reduction of assessment of chemical and other environmental impacts, we was able to gauge how this prosthetic would pretty much affect the environment. Considering this prosthetic was developed in the North American region, we ran the algorithm and found that 33% of the prosthetic is recyclable, 13% would have to be incinerated, and 54% would have to go landfill. We think these values are very conservative, but for over a duration of 4 years, that's not bad considering that a child grows constantly and we'll be using one prosthetic for 4 years. And the prosthetic only weighs 0.37 kilograms, which is very light, and the material financial impact is 4.9 on a scale of 1 to 10.
Throughout our 8 months of actually designing and fabricating a prosthetic arm, we learned the true values of communication, team collaboration, time management. Using these values, we plan on implementing them into our future work as future mechanical engineers.
Throughout the project, we've encountered a lot of challenges. With every challenge that we encountered, we pretty much gained a lot of lessons, and we pretty much had to figure out how we can overcome them. And engaging the project endeavor overall, we created our physical product. We achieved what we wanted to achieve. To see if we can create a tractable prosthetic that's possible that a child who has lost a limb can probably use for a period of time. We think the prosthetic would be marketable if manufactured in appropriate material. The tractable concept, I think, is feasible, and the functional appendage, it needs improvements. Driving mechanisms would be a major help in actually being able to make the prosthetic much more functional.
So for future work, it was noted that improvements can be made to the hand function, like Philly said. If the user wants to stick with mechanical motion, we were suggesting adding an elbow or shoulder pulley to increase the mechanical motion, and also integrating a myoelectric control system. For everyday use, we are considering for aesthetics, the user can cloak the prosthetic arm with a skin layer. Thank you.
So how does the adjustability work?
So the way it works is that there's a tensioner on the inside of this, right? We call it, we had to create our own name because it's the first time we developed it. So there's tension, you loosen the screws, and then once you loosen, it's loosened right now, and then you extend, and then you tighten it. There's a nut on the inside, and as you tighten, it extends on the inside. There's a loop with a slot in there, and it pretty much expands on the inside, on both sides, on both tensions.
Okay. And in adjustability, do you have ability to adjust the diameter?
So the way we compensate for that is the actual socket. The socket, we believe that the best way to accommodate the girth of an arm is to have the size at the maximum that you would find in the orthopedic data for that amputee. So pretty much after that, you wrap your sleeve in thicker layers and slowly adjust, as the child grows.
As the child grows. Okay, good. And then the hand size?
The hand size, so for the hand size, for a group of 5 to 8 years old, I pretty much designed to the maximum. So I took the size for a child at 8 years old. So pretty much those measurements, that at that point, the child pretty much would have met the size requirements.
Okay, and if I look down the center, point toward the other way, right around. How far in does the socket actually go?
The socket goes to this point here, right behind the tensioner. And as you can see in the earlier image, we tested a 10-pound load of the tensile loading, and the socket would not even budge. It's pretty solid.
Is there enough bite here? Is that bite enough to keep this from flexing on a person?
Yeah,
That's a question.
that socket is not budging. That socket is not budging. And ideally, we would like to weld both pieces together.
And then, is there any thoughts of future of wrist?
Yes. So the wrist that we incorporated into this is a Revolute wrist. So
this will rotate?
Yes. So this can rotate.
Good for a minute.
Yeah. So the wrist can rotate. We added that after advisor Tosin Blue told us that we needed to add rotation to the wrist. So what we did, I would love to show it. This piece right here, it's like a nub, and it's kind of like a zip. If you could think of a zip lock mechanism on the inside, and as you turn it, it pops in, it pops in.
Oh, so it's
And
like
yeah, so
like a ratchet?
Yeah, just like a ratchet, just like the gears of the fingers are ratchet, the inside of the wrist is also like a ratchet too. So it could only turn up to like 120 degrees on both, on one direction.
So the patient would with their other hand
Yeah.
rotate it and
Yeah.
then be in the right position to do that?
Yes.
Can you show me how it functions?
So how it functions is that,
How you get the fingers to move?
So-
Yeah, that's my question.
so there's gears on each finger, right? And you know,
Okay, working off the back end, can you make this thing, the fingers move?
so the way you make the individual will grasp whatever they want to, right? They'll grasp it whatever they want to while it's in a locking position, and the pins will, just like a ratchet and paw, it'll lock up, okay? And then when they want to release it, they just turn this wrist part here, and then it's in an unlocked position. And once it's in the unlocked position, the pins move back inside. There's pins in here that move back when I turn this, and then they can release. You see?
So the opposite hand operates the hand.
Yes.
It
So in other
doesn't
words-
work from the stump doesn't.
Yeah, I was
actually-
thinking you're using the arm piece to put the tension and pull.
No, we didn't. That's what we want to. In future work, we want to add some kind of mechanism that attaches to a shoulder or elbow, whereas they can withdraw their elbow or shoulder and then
And
pull.
pull.
Yes, that's what we want to add eventually.
Yeah, I guess like current prosthetics nowadays that are consisted as myoelectric, the way they work is as if they flex their triceps, they close